Welcome to this coding walkthrough. In this session, we will explore LeetCode problem number 1373, maximum sum BST in binary tree. This problem challenges us to identify the maximum sum of all keys in any valid binary search tree, BST, that can be formed within a given binary tree. Let's dive in and break it down step by step. In this problem, we are given a binary tree, and our goal is to determine the maximum sum of all keys in any binary search tree, or BST, that can be formed within the given tree. A binary search tree has a specific structure. Every node's left subtree contains only nodes with keys less than the node's key, and every node's right subtree contains only nodes with keys greater than the node's key. Additionally, both the left and right subtrees themselves must also follow the binary search tree property. If no valid BST can be formed within the tree, the result should simply be 0. The input to the problem is a reference to the root of the binary tree, where each node has a key, a potential left child, and a potential right child. The output is an integer that represents the maximum sum of keys from a valid BST within the tree. Continuing, the right child of each node is either a reference to another node or null if no child exists. The output of the problem is the maximum sum of keys that can be obtained from any valid BST within the tree. Let's look at an example to understand this better. Imagine a binary tree with the root node having a value of 1. The root has two child nodes, 4 and 3, and the left child of 4 has further children, 2 and 4. In this case, the subtree rooted at the node with value 4 is a valid BST, with a sum of 4 plus 2 plus another 4, which equals 10. This example illustrates how subtrees can be considered individually to calculate their sums if they satisfy the BST property. Another detail in this example is that the subtree rooted at the node with the value 3 is also a valid BST, but its sum is only 3. The entire tree, however, is not a valid BST because the right child of the root, which is 3, is less than the root value, which is 1. Therefore, the maximum sum comes from the left subtree rooted at 4, which gives us a total of 20. Now, for a different example, consider a tree with the root value of 4 and children 3 and 8. The left child of 3 is 2, and the right child of 8 has two children, 6 and 9. In this case, the entire tree itself forms a valid BST. Summing all the node values, we have 4 plus 3 plus 2 plus 8 plus 6 plus 9, which equals 32. Since the entire tree is a BST, the maximum sum comes from the entire tree. Now, let's consider a scenario where all the node values are negative. For example, a tree with a root value of -1, and two children -4 and -3. In this case, no valid BST can have a positive sum because all values are negative. Therefore, the output is 0. This shows that even though a subtree might satisfy the BST property, its sum must still be positive to be considered for the maximum sum. The constraints for this problem ensure that the number of nodes in the tree can go up to 40,000, and the values of each node can range from -40,000 to 40,000. Additionally, a subtree must strictly satisfy the BST property to be included in the sum calculation. If no valid BST can be identified, the output will be 0. There are a few edge cases to keep in mind. First, if the tree consists of just a single node, that node is always a valid BST, and the output will simply be the value of that node. For example, if the input is a tree with a single node valued at 5, the output is 5. Second, if all nodes in the tree have negative values, the output will be 0 because no valid BST can achieve a positive sum. Third, if there are duplicate values in the tree, those duplicates may violate the BST property, and such subtrees should be excluded from the sum calculation. Finally, for very large trees with up to 40,000 nodes, the solution must be efficient and handle the constraints effectively. These considerations ensure that the solution works correctly across all scenarios. To tackle the problem of finding the maximum sum of all keys in any binary search tree within a binary tree, several approaches were considered. One straightforward method is the brute force approach. The idea here is to systematically examine every possible subtree within the binary tree. For each subtree, we verify whether it satisfies the BST property by ensuring that all nodes in the left subtree are smaller than the root and all nodes in the right subtree are larger. If the subtree qualifies as a BST, we compute the sum of its nodes and compare it with the maximum sum tracked so far. However, this approach comes with significant drawbacks. For each subtree, we must repeatedly validate the BST property and calculate its sum, which requires O(n) time. When applied to all subtrees, this results in an overall complexity of O(n squared). This makes the brute force method impractical for large trees due to its inefficiency and redundant calculations. A more effective solution is the optimized approach, which uses post-order traversal to streamline the process. Post-order traversal processes the left and right subtrees before addressing the root node, which is ideal for gathering and propagating necessary information. With this approach, we can determine whether a subtree is a BST, calculate its sum, and identify its range of values, all in a single traversal. The key insight is that a subtree is a valid BST if the maximum value in the left subtree is less than the root value, and the root value is less than the minimum value in the right subtree. This ensures that the BST property is maintained. By propagating this information up the tree during a single post-order traversal, we can efficiently validate BST properties and compute sums without redundant checks. Each node returns a tuple containing whether the subtree is a BST, the sum of its nodes if it is, and its minimum and maximum values. Additionally, we track the global maximum sum of valid BSTs. This approach has a time complexity of O(n), as each node is visited exactly once, and it eliminates the inefficiencies of the brute force method. After evaluating both methods, the optimized approach using post-order traversal was chosen due to its efficiency and clarity. This strategy ensures that all necessary data about child nodes is available before processing the parent node, avoiding redundant calculations. Comparing the two approaches, the brute force method, while conceptually simple, is computationally expensive with its O(n squared) complexity, making it unsuitable for large inputs. In contrast, the optimized approach operates in O(n) time, allowing it to scale effectively to handle constraints like node values in the range of -10,000 to 10,000 in trees with up to 10,000 nodes. Both methods share the same O(h) space complexity, where h is the height of the tree, since they rely on recursion. However, the optimized approach is significantly more scalable and avoids the need for additional data structures to handle redundant computations, making it the clear choice for this problem. The pivotal realization that made the optimized approach possible was the combination of BST validation and some computation during a single post-order traversal. By propagating critical information, such as whether a subtree is a BST, its sum, and its range up the tree, we could validate and calculate efficiently in one pass. This was the key to eliminating the inefficiencies inherent in the brute force method. The final solution demonstrates how leveraging traversal orders and carefully managing information during recursion can transform a complex problem into an efficient, elegant algorithm. The optimized approach not only achieves the desired results efficiently but also highlights the power of algorithmic insights in solving real-world computational challenges. In this problem, we are tasked with finding the maximum sum of all keys in any valid binary search tree, or BST, that can be formed within a given binary tree. A subtree is considered a valid BST if it satisfies the BST property, meaning that for every node in the subtree, the values in the left subtree are strictly less than the node's value, and the values in the right subtree are strictly greater. To solve this problem efficiently, we will use a bottom-up approach with recursion, specifically a post-order traversal. This traversal pattern, which processes nodes in a left-right root order, allows us to evaluate each subtree only once and determine whether it's a valid BST while simultaneously calculating its sum. The first step is to define a helper function called DFS, which will perform the recursive traversal. For each node, this function will determine three things: whether the subtree rooted at that node is a valid BST, the sum of all nodes in the subtree if it's valid, and the minimum and maximum values in the subtree to verify the BST property. Additionally, we define a base case for the recursion to handle null nodes, which represent empty subtrees. In the base case, if the current node is null, we consider the subtree to be a valid BST because an empty tree satisfies the BST property by definition. The sum of an empty subtree is 0, and we use infinity for the minimum value and negative infinity for the maximum value to ensure that comparisons with actual node values work correctly. Moving to the recursive step, we compute the results for the left and right subtrees by calling the DFS function on the left and right child nodes of the current node. To check if the current subtree is a valid BST, we verify two key conditions. First, the left subtree must be a valid BST, and its maximum value must be strictly less than the current node's value. Second, the right subtree must also be a valid BST, and its minimum value must be strictly greater than the current node's value. If both conditions are met, the current subtree is a valid BST. In this case, we can compute the sum of the subtree, which is the sum of the current node's value and the sums of the left and right subtrees. If the subtree rooted at the current node is a valid BST, we also update the global maximum sum if the new subtree's sum is greater than the previous maximum. Then, we return updated information for this subtree, that it is a valid BST, its total sum, and its updated minimum and maximum values. The minimum value is the smaller of the left subtree's minimum and the current node's value, while the maximum value is the larger of the right subtree's maximum and the current node's value. On the other hand, if the subtree is not a valid BST, we propagate invalid values up the recursion chain. Specifically, we return that the subtree is not a BST, assign its sum as 0, and do not use meaningful minimum or maximum values for further comparison. To track the maximum sum across all valid BSTs during the traversal, we maintain a global variable called max_sum. Once the traversal is complete, this variable will contain the result, the maximum sum of any valid BST in the binary tree. The post-order traversal is critical for this approach because it ensures we process the left and right subtrees before evaluating the current node. This bottom-up strategy is what allows us to verify the BST property efficiently. By propagating the minimum and maximum values of the left and right subtrees, we can avoid redundant computations and verify the BST property in constant time for each node. The algorithm is optimized for a single pass through the tree, making the time complexity O(n), where n is the number of nodes in the tree. Each node is visited exactly once, and all the necessary computations such as checking the BST property and calculating the subtree sum take constant time per node. The space complexity is O(h), where h is the height of the tree. This accounts for the maximum space used by the recursion stack in a depth-first traversal. Edge cases to consider include an empty tree, which results in a sum of 0 as there are no valid BSTs, and the case where the entire tree itself satisfies the BST property, in which case the sum of all nodes is the result. Let's walk through an example to clarify the algorithm. Consider a binary tree with the root node 1, which has 2 children, 4 on the left and 3 on the right. The left child 4 has 2 children, 2 and 4, while the right child 3 has a single right child, 5. Starting with the leaf nodes, we process the nodes 2, 4, and 5. Each of these nodes is a valid BST, and their sums are simply their values. Next, we evaluate the subtree rooted at the left child 4. This subtree is not a BST because the right child, which is 4, is not strictly greater than the root value of 4. On the right side, the subtree rooted at 3 is a valid BST with a sum of 8, as it satisfies the BST property. Finally, at the root node 1, the entire tree is not a BST because the left child 4 is greater than the root value of 1. The largest valid BST is the subtree rooted at 3, so the result is 8, the maximum sum of all valid BSTs in the tree. This solution determines the maximum sum of all keys in any valid binary search tree, BST, within a binary tree using a depth-first search, DFS, approach. The function maxSumBST starts by initializing self.max_sum to 0, which will store the maximum sum of any BST found. The helper function DFS processes each node recursively. For a null node, it returns true, INF 0, because a null node is trivially a BST, with extreme values for min/max and zero sum. For non-null nodes, DFS computes the properties of the left and right subtrees, whether they are valid BSTs, their minimum and maximum values, and their sums. The current node subtree is a BST if both left and right subtrees are valid BSTs, and the current node's value is greater than the maximum value in the left subtree and less than the minimum value in the right subtree. If this condition is met, the sum of the current subtree is calculated and compared to self.max_sum. The function then returns updated values for the current subtree, whether it's a BST, its minimum and maximum values, and its sum. If the current subtree is not a BST, the function returns false, 0, 0, 0 as dummy values. Finally, the maxSumBST function returns the value of self.max_sum, which contains the maximum sum of any valid BST in the binary tree. This solution efficiently traverses the tree in O(n) time, where n is the number of nodes, ensuring each node is processed once. Here, we start with the definition of the treeNode class, which represents each node in our binary tree. It includes an integer value, val, and references to its left and right child nodes. We also provide multiple constructors to initialize a node with or without specific values in child nodes. Moving on to the solution class, we define a private variable maxSum to keep track of the maximum sum of any valid binary search tree within the given binary tree. The main method, maxSumBST, initializes maxSum to 0 and calls the recursive DFS function, starting with the root of the binary tree. Finally, it returns the value of maxSum after the traversal is complete. The DFS function will handle the heavy lifting of validating subtrees and calculating their sums. The DFS function is designed to return an integer array containing 4 key pieces of information, whether the subtree is a BST, the minimum and maximum values in the subtree, and the sum of all its nodes. For a null node, we return an array indicating that it's trivially a BST, with extreme values for min and max, and a sum of 0. Next, we recursively call DFS on the left and right child nodes to gather their respective information. We then check whether the current subtree satisfies the BST properties by ensuring both child subtrees are BSTs and that the current node's value falls between the maximum value of the left subtree and the minimum value of the right subtree. If these conditions are met, we calculate the current subtree sum by combining the left and right subtree sums with the current node's value, update maxSum if this sum is larger, and return the updated information. If the subtree isn't a BST, we return a failure state with default values to indicate the invalidity. Here, we start with a simple binary tree where the root node is 1, and it has 2 children, 2 on the left and 3 on the right. To determine the maximum sum BST, we perform a depth-first search, beginning with the root node, 1. First, we move to the left child, 2. Since 2 has no children, both its left and right subtrees are none, so we return the base case values. The subtree is a valid BST, with minimum and maximum values set to infinity and negative infinity, and a subtree sum of 0. Now, we check if node 2 forms a BST. Since there are no violations of the BST properties, 2 is a valid BST. The subtree sum for node 2 is simply its value, 2. We also update self.max_sum to 2, as this is the largest sum we've encountered so far. Moving to the right child, 3, we repeat the same process. Like 2, node 3 is also a valid BST with a subtree sum of 3. We update self.max_sum to 3, as it is now the maximum sum found so far. Next, we return to the root node, 1, and check whether it forms a BST with its left and right subtrees. For a BST, the maximum value from the left subtree must be less than the current node, and the current node must be less than the minimum value from the right subtree. Here, the left subtree has a maximum value of 2, and the right subtree has a minimum value of 3. However, 2 is not less than 1, so the tree rooted at node 1 is not a BST. Therefore, we return values indicating that it is not a BST, with a sum of 0. The final output for this example is the maximum sum we recorded, which is 3. Moving to the next example, we now have a more complex tree where the root node is 4. The left subtree consists of nodes 3 and 1, while the right subtree consists of nodes 8, 6, and 9. Starting at the root, we perform a depth-first search and first explore the left subtree. In the left subtree of 4, we start with node 3 and move further down to its left child, 1. Node 1 is a leaf node, so it is a valid BST with a subtree sum equal to its value, 1. Returning to node 3, we now have the results for its left subtree, while its right subtree is none. Since there are no violations of the BST property, the tree rooted at node 3 is a valid BST. The range of values in this subtree is from 1 to 3, and the total sum is 4. Moving to the right subtree of 4, we evaluate node 8 and its children, 6 and 9. Both 6 and 9 are leaf nodes, so they are valid BSTs with sums of 6 and 9, respectively. At node 8, we verify that the BST property holds. The maximum value from the left subtree, 6, is less than 8, and 8 is less than the minimum value from the right subtree, 9. The subtree rooted at node 8 is a valid BST, with a sum of 23. Finally, we return to the root node, 4. At node 4, the left subtree is a valid BST with a sum of 4, and the right subtree is a valid BST with a sum of 23. We verify the BST property, the maximum value from the left subtree, 3, is less than 4, and 4 is less than the minimum value from the right subtree, 6. Since this condition is satisfied, the entire tree is a valid BST. The total sum for the tree is 4 plus 23, which equals 31. We update self.max_sum to 31, as it is the largest sum found so far. The final output for this example is 31. In the last example, we examine a tree where the root node is 5. The left subtree contains node 4, while the right subtree contains node 6 with children 3 and 7. Starting at the root, we evaluate the left subtree. Node 4 is a leaf, so it is a valid BST with a sum of 4. Next, we explore the right subtree of 5, starting with node 6. To analyze the time complexity of our solution, we start with the depth-first search traversal, or DFS, which is the core of the algorithm. Here, the number of nodes in the binary tree is represented by n. During the traversal, each node is visited exactly once, and for every node, the DFS function performs a constant amount of work. This includes operations such as comparisons, arithmetic calculations, and returning tuples. Since the function is called once per node, the total operations required for the traversal are proportional to the number of nodes, giving us a time complexity of O(n). Additionally, at each node, we check whether the BST property is satisfied by using conditions like left_max node.val right_min, and we update variables such as min, max, and sum. These checks and updates are also constant time operations, meaning they don't add to the overall complexity. Combining these factors, we conclude that the time complexity of the traversal is O(n). Now let's look at how this time complexity holds across different scenarios. In the best case, even if the tree is empty or none of the nodes satisfy the BST property, we still need to visit every node to verify the structure. Therefore, the time complexity remains O(n). For the average case, consider a balanced binary tree of height h. Here too, the DFS traversal visits all nodes exactly once, keeping the complexity at O(n). Finally, in the worst case, when the tree is completely skewed, meaning all the nodes form a single long path, we still visit each node once. So, regardless of the tree's shape, the time complexity stays O(n). This is because each node contributes a fixed amount of computation, and no additional overhead is introduced. The mathematical reasoning is straightforward: each node is processed once, with constant time operations, leading to an overall time complexity of O(n). The space complexity of the algorithm is driven by the memory used for the recursive call stack during the depth-first traversal. In the worst-case scenario, where the tree is completely skewed, the recursion depth equals the number of nodes in the tree, n. This means the recursive stack could consume up to O(n) space. On the other hand, the algorithm also uses a constant amount of memory for additional variables like left_min, left_max, and left_sum. These variables are reused for each node and do not depend on the tree size, contributing only O(1) to the space complexity. For the best case, when the tree is balanced, the recursion depth corresponds to the height of the tree, which is O log n. Similarly, in the average case, for a randomly structured tree, the depth of recursion is proportional to the height, which is still O log n. However, in the worst case of a fully skewed tree, the recursion depth reaches O(n), resulting in O(n) space usage. When we combine these observations, the overall space complexity of the solution is O(h), where h is the height of the tree. In the worst case, when the tree is completely unbalanced, the height equals the number of nodes, which gives us O(n). In the best or average cases, where the tree is more balanced, the height is proportional to log n, resulting in O log n space complexity. To put this in perspective, let's compare it to a naive or brute force approach. A naive solution would involve checking every possible subtree within the binary tree to determine if it satisfies the BST property and calculating its sum. For a tree with n nodes, the number of subtrees can be O(n squared, and verifying if a subtree is a BST takes O(k) time for a subtree with k nodes. This results in an overall time complexity of O(n cubed in the worst case. In contrast, the optimized DFS solution avoids this inefficiency by calculating BST properties and subtree sums in a single traversal, achieving the optimal O(n) time complexity. To summarize, the brute force approach has a time complexity of O n cubed and a space complexity of O n, which is highly inefficient for larger trees. On the other hand, the optimized DFS solution achieves a time complexity of O n and a space complexity of O h, where h is the height of the tree. This makes the DFS solution both time efficient and space efficient. The key takeaway here is that the optimized approach is particularly well suited for large binary trees, where the number of nodes, n, can be as large as 10 to the power of 4. By leveraging post-order traversal to evaluate BST properties and calculate subtree sums simultaneously, the algorithm ensures that we achieve the best possible performance for this problem. One of the most common mistakes when solving this problem is misidentifying the properties of a binary search tree. Many people only check whether the left and right child nodes satisfy the condition relative to the root, but they forget to validate the entire subtree. For example, all nodes in the left subtree must be less than the root, and all nodes in the right subtree must be greater than the root. Neglecting this can lead to incorrect results, especially when subtrees violate BST rules. Another frequent issue is overlooking edge cases. For instance, a tree with just one node is always a valid BST, yet some solutions fail to account for this simple case. Similarly, trees with negative values can also form valid BSTs, but these values are sometimes mishandled. Additionally, some binary trees may contain subtrees that are invalid as BSTs but still include smaller valid BSTs within them. It's crucial to account for these scenarios. Lastly, errors often arise from improperly handling null nodes in recursive solutions. If you assume non-null nodes during traversal, you risk runtime errors. Inefficient tree traversal is another pitfall. Recalculating properties like minimum, maximum, and sum for each subtree multiple times can significantly increase time complexity. Instead, a post-order traversal approach, where you calculate and propagate these properties in one pass, is much more efficient. Another critical aspect to watch out for is ignoring the constraints. The problem specifies that the binary tree can have up to 40,000 nodes, so any solution with a time complexity higher than O n will likely time out on larger test cases. An efficient approach is essential here. From an interview perspective, this problem is an excellent opportunity to demonstrate modular thinking. An optimal solution typically involves creating a helper function that returns multiple properties for each subtree, such as its minimum value, maximum value, sum, and whether it is a valid BST. This modular design enables efficient decision-making at each node. Post-order traversal is the natural choice for this problem because you need to process child nodes before determining whether the current node forms a valid BST. Be ready to explain this traversal choice if asked during an interview. Additionally, interviewers often explore your handling of edge cases, so you should be prepared to discuss how your solution handles scenarios like a tree with a single node, trees with negative values, or completely invalid BSTs. Lastly, spacetime trade-offs are a common topic during interviews. While a recursive solution with O, h, space, where h is the tree's height, is standard, you might be asked whether further space optimizations, such as converting to an iterative approach, are possible. This problem also shares similarities with a few related problems that you may encounter. For example, LeetCode problem 98, validate binary search tree, focuses purely on checking if a tree satisfies the BST properties. Then there's LeetCode problem 333, largest BST subtree, which asks for the size of the largest BST subtree, rather than its maximum sum. Another relevant problem is LeetCode 124, binary tree maximum path sum, which involves finding a maximum sum in a binary tree but without the BST constraint. Finally, LeetCode 543, diameter of binary tree, is another tree-based problem that uses post-order traversal and requires returning multiple values, making it a helpful practice problem for mastering similar techniques. When it comes to alternative approaches, the brute force method is one option. This involves checking every subtree to see if it forms a BST and then computing its sum. While this method is conceptually straightforward, it has a time complexity of O n squared, in the worst case, making it unsuitable for large trees. The trade-off is that it's easier to implement but lacks scalability. A more efficient approach is optimized post-order traversal, where you compute and propagate properties like the minimum, maximum, sum, and whether the subtree is a valid BST, all in a single pass. This method achieves O n time complexity but requires careful implementation to get all the details right. Another alternative is dynamic programming on trees, where you use memoization to store the results of already computed subtrees. While this can help eliminate redundant calculations in some scenarios, it is less intuitive than the post-order traversal approach and may increase space usage. Each of these methods has its own trade-offs, so understanding their strengths and limitations is key to choosing the right approach for the given constraints. Great job following along. To summarize, we tackled the problem by leveraging post-order traversal to validate BST properties and calculate the maximum sum efficiently. Remember, mastering these techniques will greatly enhance your problem-solving skills for tree-related challenges. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!